Hello and welcome back to the third lab in Unit 4. This is section 4.3, Modeling. In today's lab we're going to be developing a number of models for the bike sharing dataset. Let's quickly recap what we saw in the previous lab. It would be a good idea for us to just quickly recap a couple of these visualizations and add a few more pointers. For instance, if we wanted to see this visualization more clearly, we could resample the line plots for each signal using a pandas resample function. So let's say I resample temperature to a daily resolution. Beg your pardon, we're already looking at daily, so monthly resolution or weekly resolution. So it'll take the aggregate of all values in the week, which are all daily values in the week. You'll need to give it some kind of an aggregation function, which could be a sum, or it could be an average, could even be a median, or the mode, etc. Let's just go with the average, so mean. And if we run this, then we should see temperature as the weekly average, which makes this a bit more palatable and understandable. Let's say we do the same to a temp, and now we can start to see the difference in the summer period, which we were looking at between temperature and feels like temperature in the previous lab as well. And we can start to see the alignment in the winter months better as well. So for wind speed, maybe we can try something different. Monthly mean. You see it's a fairly low resolution, so perhaps weekly is a good idea. We could also check out the median. So the median value for each week, the mode, the maximum, the more oft repeated value. That doesn't exist. Okay. Standard deviation. Yeah, so we can even aggregate and just take the standard deviation. A better way of doing this would be to plot this in a violin plot. So let's draw a violin plot over data and see what we see here. So that's giving us a number of violin plots. What we can do is change this list to our desired list of columns: temp, a temp, wind speed, and humidity. And now we see the range of these as well as the distributions by modality in temp and a temp for summer and winter. Wind speed is more unimodal with a long tail. So is humidity, which is again slightly flatter but still unimodal with one peak, flat peak, and a long tail in the other direction. If we change this to a box plot, we can start to see what those outliers look like. So humidity has not so many outliers, whereas wind speed has quite a number of outliers. And perhaps over here, if we were to use the quantile method of removing outliers, we could perhaps use wind speed to demonstrate that. So that's wind speed, it's giving us a number of outliers here. And if we say that data wind speed should be less than the threshold, in this case we can put the threshold as something more relevant to wind speed. Let's put that back to 0.99 even, so anything below the 99th percentile. We still see the outliers. Let's change this to 95. and that's it. So according to the empirical rule, we have removed the third standard deviation around the mean. And now if we check the violin plot instead of box plot, we will see that the tail has been removed. I believe that covers most of what we talked about, and anything additional that I wanted you to learn as well. These are methods that you can use to examine the data closely. So we've learned two new techniques. One would be to resample the line plot by taking the signal and resampling it to weekly, monthly resolutions with some kind of an aggregate function. And then we tried to see if we could remove the outlier in the scatter plot, played around with the quantile based method of thresholding and removing all points below a particular quantile or percentile. And then we went into violin plots and box plots to actually see a removal of those outliers. There are better ways of doing this with different libraries and packages, and we'll get to that in the next labs. So let's restart and move to modeling. You can go into kernel menu and select restart and clear output, which will restart your entire notebook. So now you can see that there are just the cells of code and headings marked down, but nothing else. All the output's been deleted, the kernel's been restarted. Let's load this again because we want to bring that data. Now that we have the data, we can move directly to modeling. So let's build our first model. It's a linear regression model. We'll be using lasso regression, which is a type of regularized regression. We can either build a linear model without any regularization term, or we could build a regularized regression, which is going to make sure that the model that we build doesn't overfit our training data. And we can do it in a number of ways: lasso or ridge regression. In either case, basically a term is added to the regularization equation, and alpha is a parameter, or the regularization parameter, that dictates how much of that term is going to impact our model. So if we say 0.1 alpha, this is essentially setting the regularization term to have a low impact as opposed to 0.9 or 1. Linear model is a package that we can import from sklearn. The linear model contains both ridge and lasso, as well as linear model regression. We're going to be calling that with the right alpha value, in this case 0.1. So we want to regularize to make sure we don't underfit, but also we don't want it to be too constraining either. We fit the model by calling model.fit, and this takes the x train and y train, x train being the 80% of our features data set, which has our selected numerical features, as well as y train that being the target variable, or y label, y class, which is count in our case for this model. We call model.predict on x test. X test is the remaining 20% from features, and this essentially has y test, which are the ground truth labels we have. Once we've made the predictions, we can actually set or calculate the score for the model, the R2 score or R squared score statistic, which is going to tell us how well our model is covering the variance in the data set for the training set as well as the test set. So let's run this. So we can see here we built a lasso regression model with the alpha parameter regularization parameter set to 0.1. Model score, R squared score, is 0.51. So essentially we're fitting around 52% variance in the training set, and we're fitting 55% variance in the test set. This may be because the test set is a fifth or a fourth of the training set in size. Let's see if we change the regularization parameter to 0.9, what happens then. Okay, so basically it is almost very comparable, with a tiny bit of negligible impact on the variance being covered. If we make it a complete 1, okay, same, let's bring it down all the way to 0. With alpha 0, this algorithm does not converge well. You're advised to use the linear regression estimator. Makes sense, because if we're saying alpha 0, then we're not using the regularization term, and we might as well just use the unregularized version, which is just a linear model. So if I just say here linear regression, get rid of that, then there is no regularization happening here, and we have a very similar model really. Because the data set is so small, it's not impacting us. Let's go back to lasso with the alpha 0.1. And before we move forward to evaluating the R squared, let's take a look at the equation for it. We see predicted value of y equals a, which is the intercept term for the line equation, plus b, which is the line slope, multiplied by x, which is given the data set or the feature, and then epsilon, which is the regularization controlled by alpha. So let's say we're looking at temperature in our training set, a feature that comes in, we know the slope, or we calculate this slope. This is the parameter, the regression weight, and the intercept term. This is calculated by the regression model, and we want to be able to control or constrain this so that it doesn't overfit and selects the best features from all of the features. So how do we evaluate? Let's print some scores. Let's calculate the R squared statistic or R squared score on y test against predictions. So predictions that our model made against ground truth. And then we can do mean squared error as well. So it'll take each point and check the prediction, how far it is, take the square of that point, do it to all of the points, and then take the average of this, those points. So we see here R squared score 0.5516, exactly the same as what we calculated using model.score on X test, Y test. This makes sense, and the mean squared error is right now 1797970. Let's go ahead and calculate some additional metrics. Now mean absolute error, which is going to be the same unit rather than the squared unit. It'll be the exact same unit as in the rental bike count. We run it on the ground truth as well as predictions in the same way. The mean squared error, which is what we've already calculated, but in this case we're saying the squared needs to be false, so that it's actually root mean square error, and it's the square of the mean squared error, so the unit becomes correct as well. The mean absolute percentage error giving us a magnitude of error between the prediction and the ground truth as well. So when we print these out, we see 1143 as the mean absolute error, which essentially tells us that the model is on average 1143 or 1143.69 bike rentals away in either direction from ground truth on average, which is not great. Root mean squared error is saying even more, which is 1340 or 1340.88, and mean absolute percentage error is even above 100% or 1, so it's fairly large as well. So it tells us that our model is only covering 55% of the variance in the data set. It's not a great model, and we can see that the error is quite large as well. So let's look at the coefficients, or in other words, the parameters or weights that have been trained and estimated by the regression model by training on the data. We take model, which is where we have stored our regression model here. We bring its coefficients out by referring to its attribute coef underscore, we say that the columns in this new data frame coefficients must be called coefficients. It's going to have one column. The index should be the name of the columns in xtrain. We use this new data frame to plot a horizontal bar plot, giving it some figure size, a title, and then we run a vertical line which is running at x equals 0, so that any weights that are negative, in case the slope is negative, will show on the left hand side, and anything that's positive will show on the right hand side. And we do an adjustment of the subplot to bring it to the left, just to make it more presentable. So here we see for our lasso regression model, we have 4 features that are on the negative side: wind speed, humidity, which essentially means that some degree of impact is there, and that's an inverse relationship between wind speed and rental count. So when wind speed is high, rental count is low. When humidity is high, rental count is low. Conversely, when wind speed is low, rental count is high. When humidity is low, rental count is high. On the other hand, when you look at temperature, then there's a positive relationship, or a direct relationship rather than inverse relationship. In this case, when temperature is high, count of bike rentals increase as well. Similarly for weather as well, but we don't get a good sense of the magnitude in this case because all of our features have different units. If you recall, some of these units are, let's say, 1, 2, 3, 4, 5, 6, or 0 to 6 for a weekday. Working day is either a 1 or a 0. Weather situation, I think there's 3 or 4 values in there. Season has 4 values. Temperature goes between 0 and 1. A temperature as well. Humidity goes between 0 and 1. Wind speed goes between 0 and 1. And we know that the count can go up in the thousands. So let's scale our coefficients and view them again. So here we scale it by calling a new module in sklearn called pipeline. We import make pipeline function from it. From sklearn pre-processing module, we get a standard scaler, which is going to standardize it using the z-score. So when you capture the mean of any feature and divide each value by its mean, then you're essentially bringing it to unit variance so that it moves between 0 and 1. And this is exactly what's been done to the temperature and humidity and wind speed features already, as we found in the bike sharing dataset. So we can do that ourselves by using standard scaler as well. We make pipeline by calling a standard scaler and then build a lasso model as well. We fit it on xtrain and ytrain, and now we are essentially scoring it again on xtrain, ytrain by looking at the training data score of r squared and then checking it on the test data as well. We create a new coefficients data frame in the same way by calling coefficients and putting that in a new data frame and then plotting those. So if we run this, we see that the magnitude at scale, or once it's been standardized for all, is a bit more representative. And here we start to see that the impact actually of temperature and seasonality is a lot more compared to wind speed, etc., which in this case previously we thought wind speed was quite impactful in weather situation and holiday weren't. If you go down, holiday in months still are not so much as opposed to weather situation, which now seems more involved, and weekday and working day as well. Now we can do some cross validation here, because training and testing on a split data set is good enough, or well and good. We want to run it multiple times in several iterations, and cross validation allows us to do that. If we select cross val score and cross validate or repeated k-fold from model selection module and in sklearn library, we can actually evaluate the model using cross validation by just giving it the model and the features and the target instead of xtrain and ytrain, because it's going to create those folds automatically. We tell it how many times it needs to run, we say 5, and then some kind of a scoring metric. In this case we say negative mean squared error. Now of course that's a bit counterintuitive, because mean squared error cannot be negative. The reason why we square it is to remove the sign on the distance or the magnitude from the prediction and the prediction and between the prediction and the ground truth. So the reason why we see this negative here is because this is done on purpose, since the cross-val score is going to maximize, and the optimization is a maximization function. Therefore, to maximize error wouldn't make sense, but to maximize negative error would make sense, and that's why it's a negative mean squared error. When it calculates this, we put it in a variable called CV scores, and we take the mean of those scores and put a negative sign to inverse the sign again, and we get the average cross-validation score in the right way around, and we print that. So this is going to run for 5 times. Since the data set is not so big, it's probably going to take not so long. We need to import, and we see that the cross-validation score is actually this is a squared, so we can actually say so if we take a square root of this, we'll get an idea of the magnitude is even bigger. So it's actually overfitted, because when we run it in 5 folds or 5 times, then the magnitude has actually increased from what we saw previously as 1150 or thereabouts, and as well as 1340 to 1997. So 1143 and 1340 to 1997. So coefficient importance can be plotted if we run cross-validation using cross-validate, provided features X test and Y test, or we could provide it features and target. We say that we want to cross-validate using repeated k-fold, in this case, and split 5 times and repeat 5 times. Return estimator as true, number of jobs 2, and we again put it in a coefficients data frame. In this case, because we have repeated k-folds involved, we will have multiple models coming out. So we take the final model here and we run a list comprehension to say, for the final model, all the coefficients for model in CV underscore mode, which is the output from cross-validate, take the estimator. So from all of the estimators, it's taking the final one, and then it's running it on X-train columns. We can change that to features. It's putting it in a figure, a box plot, orientation, horizontal, data as coefficients, setting the color and saturation, drawing a vertical line again at 0, labeling and title, putting a title to the plot, and then adjusting the subplot. So as you can see here, because we've run it 5 times in the cross-validation function, we can start to see a variance that is represented by the box plot. And you can see with the temperature and a temperature, this variance is actually quite large. Let's visualize this. To look at the prediction error as opposed to actual values. To do this, we import prediction error display and median absolute error, which could be mean as well, but median allows us to get the centrality of the distribution and work off of that, because it's the 50th percentile. And it's also imported from metrics module in sklearn. We do median absolute error on Y train and predict on X train. So this is giving us predictions on X train, and Y train, this is giving us a baseline. And then on the test, we already have predictions from before, which is done on Y train. X test as opposed to Y test, which has ground truth. So this is the predictions on X test against ground truth. We print those two, and then we create a figure for prediction error display from predictions, taking ground truth and our predictions, produce an actual versus predicted plot with an alpha setting or transparency set to 0.5. Give it a title regression model. For name and score in scores.items, where scores is our 2 scores from training and testing, you need to plot name and score in a loop. Set the legend as upper left, tight layout, and go. So essentially, because there's only 2 scores, this will run twice, and it will put it in the legend up there. We know that the median absolute error on the training set is 1000, median absolute error on testing set is 1063, and this is because we are running our model, which is running on scaled features. This model.predict is running on scaled features, yes. If we go and print our because this is mean and we have a median absolute error that we're using, that's why we see a lower error. So this means that the error distribution has a right tail. In a Gaussian or normal distribution, because it's symmetric, the mean, median, and mode are exactly the same point where there's no skewness. When it comes to right tail, median is to the right of mode and to the left of mean. And when it's a left tail, that is a negative skew, so positive skewness is right tail and negative skewness is left tail. When it's a left tail distribution, mode is to the far right, median in the middle, and mean is to the left of the median. In our case here, because the error is showing us a median error that is lower than the mean absolute error, that means we have an error distribution that has a right tail or a positive skew. Let's go and see what that scatter plot looks like. So predicted values against actual values, and there's a lot of noise or a lot of error there, as you can see. So it's quite clear to us that we need to increase the number of data points, firstly, because this is an underfit model. There's a whole lot of error, and our performance is not great. The R-squared score is only covering about 50% of the variance in the data set. So now that we've built the model and evaluated it hand in hand, we can actually go back and change how much data we're bringing in.